Welcome to Full Momentum and HEC-RAS Vodcast. I am your host, Ben Cary, and here joining me, as always, is Chris Goodell. And for his third time, Gary Brunner. Welcome to the show today, Gary.
Thank you. It's great to be here.
Hey, Gary. Good to see you. You're looking nice and relaxed there, like almost like you're sort of retired, huh?
I am semi-retired.
Well, that's an awesome thing, Gary. And we're happy to have you here for episode 21 of today's show. We got some really exciting technical topics. We're going to get into some discussions on tidal modeling. We're going to talk about the new features in version 6.2. But before we get into anything, Chris and I definitely want to hear about what's going on in post-retirement life.
Well, I retired the end of May. And in fact, my last act as an employee was I got to push the button that sent out the email announcing that RAS 6.0 was released. That is absolutely the last thing I did on my last day of work.
Wow.
4:30 in the afternoon.
Well, I think we need to mention too, because just to make sure everybody's aware, but Gary has worked at HEC for 30 plus years.
36.
Right? Leading the HEC-RAS team for most of that time. And so it was a big deal when you retired not even a year ago, right?
Right.
When was that?
May.
It was in May or something. Yeah. So, yeah, it's like it's almost an end of an era, but, you know, RAS will continue on without Gary, but
Yes,
Gary's moved on to other things.
Yeah, so I took 5 months off to find myself. No.
Where were you?
No, I took 5 months off and not worked at all because I told somebody, literally since I started college, because I worked the whole time I went through college, I never had more than a 2-week vacation my whole entire college/work life.
Wow.
And so I thought, well, I just want to like do nothing for a while. So I did nothing for a while and I started really liking it. But I did take up I did more fishing. I was doing more exercising. I took up photography. I've been doing a lot of photography, a lot of photo. I like wildlife photography. So I do a lot of that.
I've seen a lot of your pictures, Gary, on Facebook you like to do birds, right?
Birds, ducks, anything wildlife, but I do seem to migrate to a lot of birds and ducks and stuff like that. So
aren't ducks birds? I mean,
guess, yeah.
Well, speaking of birds, Chris and I had a really cool experience yesterday. We were out in Eastern Oregon near Malheur Wildlife Refuge, and we saw literally tens of thousands. What were they? Snow ducks? What were they called?
Snow geese. I think snow geese.
Snow geese.
Yeah, they're white with black tips on the wings.
Yeah, it was pretty spectacular.
Yeah, snow geese. Yeah, cool.
Yeah, awesome. We walked up close to them, and an entire flock just took off at once, and it was so cool watching them take off like that. I'll have to show you the video, Gary. Maybe we'll post it up here too.
So, Gary, at what point in your you said 5 months, right?
Yeah.
Vacation, were you like, you know what? I think I'm ready to start doing something again.
Well, my original plan was only to take 3 months off, but I liked it too much. So I said, heck with that. I'm going to take another months off. But then I had always planned, I worked only for the federal government right out of college. And I thought, I've never worked in private industry and I think I would like to try it. So I decided to hang my resume out and I got a few bites. Klein Schmidt was not one of them, by the way.
Put us on blast.
Yeah.
We knew we didn't have a chance, Gary. So
yeah, I didn't make an offer. So I had some interviews, which was cool. First time interviewing since 1985. So I had a lot to learn about what it's like to interview now.
Yeah.
And I got fortunate. I got 3 offers. And I went with a company called HDR, which I think you guys know.
Yeah.
And I'm just a half-time employee. So I work 50% time, which is all I wanted to do. I didn't want to work full-time. But I work in their Sacramento office. And Sacramento office is really nice. it's like 200 plus people over there when they're fully staffed and everybody's in the office from COVID, which hasn't happened since I started working. But they got a pretty big water resources group: hydrology, hydraulics, reservoirs, dam safety, lots of stuff going on there. So it's been really interesting.
Yeah, many people know Mark Forrest. I still haven't wrangled him onto the podcast yet, but I want to do that at some point. But Mark's the practice lead for H&H, hydraulics and hydrology at HDR. I think that's his title. And and I know you and Mark go back a long ways, and I'm guessing that was a little bit instrumental in getting you over to HDR, right?
Yeah, that, and the other person was originally, the reason I was going to go to HDR is because originally I was going to work for David Ford, but his company got bought out by HDR. But then a lot of people probably know that David passed away, but he and I were good friends and since conception of coming to HEC, because he worked at HEC when I started here, and he's actually one of the people that interviewed me for the job at HEC. So
wow,
yeah, so
very cool. So Gary,
so you went from David Ford from one interview, and then 25, 30 years later to Mark Forrest in another interview.
Yeah. That's it.
That's kind of funny.
So Gary,
everything's interconnected. Yeah.
So Gary, since you got to private consulting, I'm curious because you had a certain view of HEC-RAS, its applicability, its strengths, its weaknesses, working for HEC. You then go over private consulting. I'm assuming you're doing a lot of work that involves projects, tied to RAS. Did you learn anything about RAS moving into private consulting that you hadn't really thought about, or you didn't really know as much about before moving over?
Well, I kind of already knew this, but it kind of driven home is one of the things that you really need to concentrate on in the private industry is, doing things efficiently and, looking for ways to make work more efficient, easier, so forth. And because of that, a lot of people develop spreadsheets. They write their own code around RAS. They use this, they use that. And I always knew that was the case. And from my view, I tried to make RAS more efficient. Like, the whole concept of RAS is a river analysis system. It's all in one. You don't need to buy a GIS. You don't need to buy a special interface. If you want to do steady flow, unsteady flow, 2D, sediment transport, water quality, it's all right there. That was really the idea from conception. It just has taken 30 years to make it happen. So that's one thing is the consultants, because let's face it, time and money is the bottom thing in the consulting world, right? You got a client and you said you're going to do something for X amount of dollars in X amount of time, and you got to get it done.
That's right. So now you understand the frantic phone calls I'd have to you in the past, on a Friday, and begging you for help, right?
Yeah, I understand.
Yeah, that's where it comes from.
But the other thing that was eye-opening to me is that there's a lot of really smart consultants out there that have developed a lot of really cool and unique tools of their own to do their work. Okay, so that's a big eye-opener too, and seeing what other people have really developed to help them do what they do.
Totally.
Yeah, and it's great now with the ability to script with RAS and to use the HEC-RAS controller to help with that. And now you've got scripting built into RAS Mapper, where you can develop your own maps and share those scripts with others. And so that's one thing I really enjoy about where you've taken RAS is its ability to allow the user to even take it further, if they want. And you've kind of made it that
way. A lot of things, like you said, the API and programming against that, but also then the rules capability for controlling gates and stuff like that and pumps. And that's I've actually been using the rules more now outside of HEC than I had inside, because we're doing a lot of work with the California Aqueduct actually, and all the kind of gate settings there. And I was helping some young engineers write rules to control operations of the aqueduct and for different purposes. So that's been fun too.
Yeah, that's awesome. I'd be interested, even like a year, 2 years from now, to get your take on being in the consulting side of things. How does that shape your view of how RAS works and how it's set up, and what things you might have done differently having that perspective versus, working at HEC?
Yeah, I'm sure I'm going to have some different points of view. But one of the things about HEC is a lot of what happens is dictated by money.
Yeah.
It just is. I mean, you can't really, a lot of people think, HEC is government office. They just have a truckload of money. They do whatever they want. That is completely false. It's really, what is dictated is what gets paid for, and whether that's through R&D, and you have to write proposals all the time to get R&D proposals and get that through, or whether a district puts up the money to pay for a new feature. And that's how RAS really went. Okay, and so I always was writing proposals all the time for R&D money, and calling districts and writing districts and say, hey, wouldn't it be cool to have this new feature? You guys could really use this.
So Gary, you've told us stories about that before, and I remember them being pretty interesting. So is there one feature that stands out to you that RAS has, and it's due to a specific district put up the money to do it?
Oh, there's so many. I mean, the reality is that the district offices in the core paid for most of RAS.
Okay.
Yeah, I'd say at least 50%, and then R&D paid for the other 50%. So there's so many features. I mean, from pumps paid for by New Orleans district to rules paid for by, Florida, and South Florida Water Management outside the core also, and, breaching stuff paid for by, Risk Management Center, and
all the ice stuff.
The ice stuff paid for by CREL, actually. CREL, Cold Region Research Lab, wanted to use RAS, but they wanted ice capabilities to do some of their own research work, and so they funded put ice into RAS. And a guy by Steve Daly from CREL, he's retired now. He's a little older than me. he was instrumental in getting ice in RAS. If it wasn't for him, it would have never happened. So
yeah, it's pretty cool. I think a lot of people just think that it's just these mad scientists down at HEC coming up with all these ideas on their own and making it happen. But it seems like it's much more of a collaborative thing between a lot of different people all over the country. So.
And just users that don't even pay for stuff. Ideas come from users. Ideas come from us too. I've had lots of ideas, and so has Mark and Steve and Cam, and everybody in the RAS team has had ideas for cool things. But a lot of the ideas have come from users. And then we just flip the light bulb on. Oh yeah, we can do that. Yeah. We'll do it.
Yeah, what I always tell people when they say, hey, why doesn't RAS include this? I'd say, hey, send them a note. If it's easy to put in and it's interesting to them, they'll put it in. If it's a big deal, you better be ready to pay for it, though.
Yeah, that's one thing that you don't know how many times someone's come up to me and said, hey, I sent you a email like 5 years ago about a new feature and you still haven't put it in. I'm like, oh, what were you asking for? We get asked to put tons of features in, and A, you got to have funds to support it. B, it's makes sense, right?
Right.
That's the other thing, and then there's priorities. There's an endless list of features that should be in HEC-RAS that are not there.
Mm-hmm.
There literally is, just because time and money.
Well, that's a great transition, Gary, for talking about historically implemented new features, who funded it. And now we can talk about one of the exciting developments in the HEC-RAS world, which is the new release of RAS version 6.2. So I'm going to go ahead and share my screen so that everybody watching today can see these new features. If you haven't already heard, some really, really cool stuff that came out of this newest release. So I'm just going to go through these one at a time, rapid fire, and I'll let you guys chime in if there's anything you want to add or give some clarity to why this is so important to HEC-RAS as a program. So the first is we now have the ability, and this is in beta form, it looks like, to have horizontal variations in Manning's values across 2D cell faces. Correct me if I'm wrong, Gary, but previously the Manning's M value at a cell face was determined based on what the Manning's value was at the center of that cell face. Is that correct?
Yeah, that's right.
Okay, and now we have the ability to have a composite Manning's M value based on the stationing of that cell face and kind of what Manning's and roughness values line up along that face. So this seems like a pretty cool development.
Yeah, absolutely. I mean, we had always planned to do this right from the start, but for the first beta version, we thought, okay, well, let's just pick up a single N value per face, because it's a 2D model, and most of the time people are going to have smaller cells, and it won't be that bad of an approximation anyway. But after RAS was released, people started using larger and larger cells, and it was obvious that, in lots of places, especially overbank areas, people are using larger cells, and it's obvious that it should have had, multiple N values. And so this was something we always planned to do. It should have been done a while ago. So I got to give credit to Mark Jensen on this, because Mark, after I left, decided he was going to push this through, and good for him, because it's a extremely needed capability, and it's been a long time coming.
Yeah, this is great. I really like this feature, but I was really hoping to see vertical variation in values in the face. That's the one I really want to have.
That's already in the design works too, and it's going to be vertical with respect to depth.
Yeah.
Per face. But again, this was the first step, and then vertical variation with depth will be the next step. So,
because the way you brought that up, Gary, is interesting, and I have to ask, you're obviously not working for HEC any longer. You're working in private consulting. Do you still keep tabs on kind of what's coming down the pipe and have conversations with some of the folks there, or are you just like the rest of us, just kind of getting the release notes as they come out?
No, I call them all the time. Because the reality is, I'm now a user, right? And so, and like when 6.1 came out, there were quite a few bugs in it, and I was like, what the heck, and so I call them up, what's going on here? And I start just sending them bugs. But the other thing is, I worked with those guys. I hired every single one of them.
Yeah.
Okay. And I worked with them for, Mark and Steve since conception in 91. And so I go over there frequently to have lunch. Like I was there today. I had lunch with the RAS team today.
That's so cool.
So, I am going to be actually working with them under contract to do some things on RAS. So I am going to be involved going forward a little bit, but I have been involved just, by calling and contacting and talking about bugs that I found and this and that. And they've contacted me a few times with questions and things too. So it's been really good. It's been kind of a two-way street.
Awesome.
Nice.
The next feature here is all about render mode improvements. So Chris, I'll kind of let you drive the conversation on this one in terms of the improvement that was made to how results are displayed in RAS Mapper.
Well, I mean, yeah, Gary can talk more than I can on this, but my impression is it's probably a difficult thing, taking the computed horizontal water surfaces in each cell and somehow making some intelligent decision in the code to translate that to some sloping water surface. And that's great, probably, or easy to do maybe on 90% of the terrain, but you always have the terrain that screws it up, right, and makes it difficult. So I'm guessing they've just expanded the ability to provide a better surface or a more realistic surface, right, Gary?
Yeah, this change though was at a specific problem that has to do with rain on grid. So the default mapping mode in RAS is called hybrid, but it's really sloping plus a little couple offshoots for when you're near a levee, that it doesn't slope over a levee, it goes flat towards the levee and so forth. But when you have rain on grid, let's say you have a rill, and you have a kind of a V and you have some overbank that goes way up. When you have rain on grid, all of a sudden you have a water surface in every cell, but it's shallow. So every cell says, oh, there's water, I can connect it.
Yeah.
And you get these fill-ins of a rill that are way more volume than is really there, just because the sloping rendering mode is connecting water that it shouldn't be connecting because of the steep terrain slopes. Okay. Yeah. And so we were looking at various ways to solve this problem. And Alex Kennedy, I got to give him the credit, and Mark Jensen came up with some ideas on how to improve that. And that's what this is. So.
Very cool. Very cool. Next, the next feature here is, it looks like the ability for users to download USGS terrain data directly through RAS Mapper, as opposed to having to find terrain data sources independently, save those to the project folder where your RAS project is at, and then bring those in. You now can just kind of on the fly bring those in. I imagine that in most cases, it's not super detailed terrain data, but at least it's something, and it's very easy to bring in.
Well, it is going out to the USGS site where they have what they call their best available data.
Okay.
Now, sometimes that may be good data because it's newer data, but sometimes it might be a 10-meter DEM, right? Mm-hmm. And it is what it is. But a lot of times you want that 10-meter DEM anyway to supplement where you don't have really detailed data. So you want that as a kind of a base anyway.
Yep.
And so this is a great feature. And this is Cameron and Anton put this together for 6.2. So Cameron Ackerman and Anton Rotter-Siren, and I think it's great. I've used it a couple times already. It works really well, and it's going to expand. This is like the start, right? And as other online data sources can be programmed against, they'll start adding them. Now it's got to be kind of like publicly available sources to you know. The other thing I hope they do is they add just kind of a text file URL type of approach. So they'd have to make this more generic probably to do that. But if you had your own data server that you could put in a URL and do that, we did that with some other information. But that might be a little bit harder, but that would be a cool way too, because then you could add your own servers, whatever they might be, into your local RAS.
Yeah, and one that comes to mind just being in Oregon here is we have the Dogami LiDAR library of LiDAR data sets, and it'd be cool just to be able to copy paste that URL here and then be able to access all those files. That'd be sweet.
Yeah, no, this editor is doing a lot more than just downloading the data. You know, it's bringing it in and allowing you to create a train model out of it. So there's a little bit more going on than just, you know, downloading it. It's making RAS Mapper aware of it, and et cetera, et cetera. So it's pretty cool.
Yeah, I want to use that. I'm looking forward to trying that out. That sounds really cool.
Awesome.
Right.
Next here, it's all about sediment transport. So we have the sediment rating curve analysis tool. Anything special to add here to this feature?
This is Stanford Gibson's work, and Stanford's always wanted to add this sediment rating curve, and he was really jazzed to get this in. He's wanted it in RAS for quite a while. And there's a new computer science guy on the team, Zach, that worked on this. So I want to give Zach credit. And you know, this is something you need in sediment transport work to do model calibration, right? And you know, bringing in load data, et cetera. So
yeah, awesome. Then we got a couple other. Go ahead,
you
Chris.
guys who haven't seen Stan Gibson's videos, he does a great job putting out videos of all these new sediment transport features. So give those a watch.
Very cool. I like that. Thanks, Chris, for reminding folks that those are available. And then, yeah, the last couple of ones here are also awesome. Speed improvements, which are always really great for users in RAS. I'm sure everyone will be appreciative of that. We have new floodplain deposition methods. Again, that's going to be related to 1D sediment transport functions. Multiple maps. So this is kind of the idea of, instead of generating a single stored map at a time, you can now have the ability to generate multiple at a time, which is great. Then we get into one that, Chris, I know you're kind of excited about, and that is lava flows being available in RAS. You want to talk more about that?
Well, this one just like blindsided me. I had no idea this was even a thing that was under consideration. And all of a sudden RAS can do lava flows. And I started thinking, well, okay, I better start looking for work that involves modeling lava flows. I'm going to be traveling to Hawaii and the Canary Islands a lot coming up here. But Gary, were you involved in the start of this, or is this something brand new?
I had nothing to do with this at all. I imagine this is Stan Gibson and Alex Sanchez. That's what those two are probably the two that put this in. And I'm sure that somebody approached HEC that, hey, you can do mud flows, but what about lava flows? We have all these lava flows, you know, and that we want to be able to model lava flows going through, you know, towns and stuff like that we occasionally see happen.
Well, in reading this though, and Gary, I don't know, you may know the answer better, but my impression is from reading about it is it doesn't simulate the actual solidifying of the lava. So it's not going to change the terrain at all. It's just basically giving it a different viscosity and allowing it to cool and change viscosity throughout the simulation. Is that right?
Yeah.
Okay.
Yeah, but I don't know all the details either, because I was not involved in it at all. That was after I left.
I was going to say,
it is an alpha version, so it's brand new and probably buggy, I guess, huh, Gary?
I think they thought it was cool, so they probably said, hey, let's put it in 6.2 release anyway. We'll just call it alpha. Yeah. If it's alpha, that means it wasn't even tested enough to be called beta.
Yeah. Use it your own peril, basically, right?
Right. In other words, it's probably fun to try out, but you better wait for the next version when maybe maybe the next version will be beta.
I'll just say what everyone else is thinking, and that is, how did we get lava before we got depth averaged Manning's roughness? That's what I want to know.
Priorities, man.
What sounds more sexy?
Exactly.
If you're a RAS user, I think depth averaged Manning's roughness sounds pretty awesome. So
You're showing the nerd in you right there, Ben.
Yeah, it's not sexy, not at all.
Yeah, the last couple here, unsteady riprap analysis. So we now have the ability to do use a riprap calculator using unsteady flow analysis, which is really, really cool. I know that there's been a couple projects that I've been involved in where we wanted to use the riprap calculator, but we were doing unsteady flow analysis, and so now having to create a separate plan to do that is pretty sweet.
Yep.
2D bridge stability looks like some just improvements to the overall computations on how that's done. I'm sure that's one of those features, given how new 2D bridges is to HEC-RAS, that probably every version from now until 7.0, there's going to be little tinkers with how that's made and improvements to that overall computational regime.
Yeah, for sure. Yeah.
And then the last one here is kind of funny. The north arrow is now available in RAS Mapper to be added. And it feels like this was one maybe that over time, there was tens of people that were emailing Gary, what about a north arrow? What about a north arrow? And then eventually somebody's like, okay, fine, we have to eventually get
I think it was literally hundreds of people over time said, why can't you put a north arrow over on the map? So they finally did.
Fine, we'll put it in there. Stop bugging us, right?
Exactly. So overall, a bunch of cool features. I hope everybody's excited to jump in and try some of those out. Besides, the new 6.2 release, which is obviously has got a bunch of cool stuff. And I know, Gary, we've touched on this back in episodes 12 and 13 a little bit, but anything in particular that you're really excited about that might be coming down the chute over the next couple of years?
Oh yeah, there's lots of stuff. So one thing in my new job, I've been doing a lot of work in hurricane modeling. So we're working down in Louisiana Water Initiative project, and RAS, we added wind forces, but we're still kind of using combined AdCirc for coastal and RAS for kind of the boundary, to take AdCirc boundary conditions and then come inland with that. But I think HEC needs to add pressure force differential for hurricanes into RAS, and that would be an easy thing to do. And I think they actually are going to work on that. And then probably later on, well down the road, look at adding forces due to waves. Okay. And if that were to happen, then you could, RAS could pretty much be the coastal model as well as the inland model. But HEC's, even before I left, HEC's been working on a new GPU compute as an option. So a CPU compute. And I imagine the first version of that will just be 2D cells only. You won't be able to have hydraulic structures. And then they'll probably add structures later. But a GPU compute could dramatically speed up the computations, 10 to 100 times for these larger models where you're doing rain on grid modeling, especially.
Do you need to get new computers for that, Gary?
Well, there'll be a certain type of graphics card compatibility that'll be required, but all kinds of graphics cards should work. But if you want it to run faster, you can say, well, my current graphics card only has like 64 GPU cores, and I'm going to get one that has 256 or 512. Then I can run a really big data set fast, that kind of thing. So it'll depend on your use case, right? That kind of thing. Another thing that's been going on even before I left was floodways in 2D. So HEC is working on tools to try to assist in doing floodways easier in 2D modeling, which, it's a difficult subject, but it's happening. At some point, they're probably going to work on a simplified groundwater model, so you can have groundwater surface water interaction. And then right now, the infiltration capabilities in RAS are just event-based, where they subtract the infiltration from the rainfall and you get rainfall excess, and there's no further infiltration after that. And so I imagine a future version, they'll have continuous, infiltration based on the water on the land surface. But if you do that, you got to have a groundwater component.
Yeah.
In other words, otherwise you just never get any water back out. Into the river. So that's probably something that'll happen in the future.
Gary, I know a lot of people are wondering this, and I've gotten this question a lot, but is RAS ever going to have a 3D option?
Sure. Why wouldn't it, right?
Well, yeah. I mean, who would have thought 2D like 20 years ago, right?
Well, who would have thought 1D unsteady flow when we started even?
Yeah.
Mm.
A lot of people thought RAS was just a replacement for HC2, right? And
Right.
which was 1D steady.
Yeah.
But that was never the plan. The plan was to river analysis system, whatever that means, you know.
Yeah.
And obviously it has limitations, given where it's at right now. But let's face it, modeling is, you know, people are moving more and more to 2D modeling right now, right?
Mm-hmm.
It's because there's lots of software out there that can do 2D modeling efficiently now.
Mm-hmm.
Mm-hmm.
And then people are moving to 3D modeling more and more too. But for right now, still certain types of problems and limitations of size and dimensions and durations. But as computers get faster, people are going to want to do more and more 3D modeling. So yeah, RAS will have a 3D component someday. If it doesn't, I'd be disappointed.
So is it more like, Gary, is it more like 1 year out or 2 years? What do you think?
Or like 5 years out or more.
Yeah, I tell people don't hold your breath, but hey, you never know. It could come out. That's good to hear that that's something that's a possibility in the future. That's great.
I'm not saying they started on that because they haven't. I'm not saying they're fine to do it because they have. They're not. I'm just saying that's natural evolution, right?
Yep. And of course, the funding thing too, right? You
Right.
gotta be funded for
it.
Speaking of future developments that are very exciting, Full Momentum has a really cool announcement to make, and it's about a new feature that our video podcast here has, and that is we've been able to move our recordings not only onto YouTube where they are, and you can watch the video components to them, but we actually have podcast versions now on both Apple Podcasts as well as Spotify. This was a request that we had from a couple of listeners that liked to watch the videos, but they also like to listen to them on their drive to work or while they're doing some yard work. Which, man alive, if you're doing yard work and listening to talk about RAS, bless your heart. But folks wanted it, and we listened to those requests, and so now you guys have that option to listen to us on the go. So if you're interested, please go subscribe, rate, and review us if you can. We obviously enjoy all of the followers that we can get on any platform that works for everybody.
That's
great.
I
have to say your segues are on point today, and you have been you've got that down very well.
You guys keep setting me up, and I'm just taking what I get. So very cool.
Well,
we're, like I said, we're super excited to have Gary on, not just to talk about new features and other things, but we're going to get into the weeds on some technical talk. But before we do that, we're going to get into some RAS trivia. So for those of you guys who are wondering, we're going to do some RAS trivia here in a second, where we will each ask each other at least one question. I will likely be stumped by Chris and Gary, but nevertheless, I will still participate. But before we do that, let me give a quick read for our sponsor today. So we are thankful for our sponsor, Kleinschmidt Associates, who is known throughout the industry as a firm that provides practical solutions to complex problems affecting energy, water, and the environment. You can learn more at kleinschmidtgroup.com. So shouts to Kleinschmidt, as always, for sponsoring today's episode. But with that, let's get into HEC-RAS trivia. I will go ahead and start us off so that I can't be embarrassed to start off this segment. So
okay, what are the ground rules? What are the ground rules here?
So the ground rules for the trivia game today, I'm glad you asked, Chris. So each of us will ask one question at a time, and we'll go around. We'll give each other 10 seconds to think about the answer, and then whoever asks the question will ask each individual what their answer is. It'll be honesty policy in terms of what your answer is, and then the person asking the question will reveal the correct answer. And there will be no scoring, because I do not want my record posted online. So this first question for you guys probably will be a softball, but I'm interested if you can get the exact timeline here. So, and actually, this is from an online resource that I'm not 100% sure is correct, but I hope it is. So HEC-RAS added 2D modeling with the version release of HEC-RAS 5.0, correct?
Yes.
Theta.
Okay. What year? No, this is version 5.0. So what year and what month was HEC-RAS 5.0 released? So
wait. Before you answer, are we talking about 5.0 official release or 5.0 beta?
5.0 official release.
Okay. Did you say year and month?
That's what he said.
Oh my gosh. That's
This is
not
a
a
big deal.
softball.
This
I
is a
mean,
big deal.
I know the range, but I'm not going to get the month.
That's okay. You can get partial credit. You can get
Okay,
partial
let me
credit.
think about this. Gary, it looks like you know.
No, I know the year, of course. Okay, and I think I know the month, but I'm actually not certain. I don't remember the exact month, to be honest, but I think I know it.
Okay,
well,
I'll have
Gary,
a guess. I'm going to guess.
Why Chris is thinking, Gary, why don't you give us your guess?
So the year was 2015 for sure, but I think the month was March, but I'm really not sure of that at all.
Okay, so my guess was going to be 2014 November, but I you know, between the beta and the full release, it's a little hazy for me. So 2014 November, that's my guess.
You guys were both close. Gary, you were closest. So the correct answer is February 2015.
So. Are you sure? Wait a minute. Are you sure the manual doesn't say February, but we didn't actually release it until March? Because that has happened.
There's some gray here for sure.
Yeah.
That's
all right,
a good
Chris,
one.
why don't you go next?
All right. So I've got a bit of a nerdy one. All right. But I think, Ben, if you think deeply on this, you may be able to get this. And Gary, I don't know, you may know it, you may not.
When you say think deeply, do you mean like think into Google and ask the question, or?
Exactly. That's what I did. All right. So, as you both know, that in unsteady flow modeling, both 1D and 2D, RAS has to use matrix solvers, right? To solve the series of equations that are developed from the conservation of momentum and conservation of mass, right? So there are many options. The default in 1D is the Barkow, right? Or the skyline matrix, right? And the default in 2D is the Paradiso, which everybody calls it Paradiso, but it's the Paradiso. So my question to you guys is, what does Paradiso stand for? And I'll give you a hint. It's 3 words. It's an acronym. What does Paradiso stand for? Pardiso. Ben looks like he's about to have a meltdown here.
I'm going to say pair of 2 solvers. Paradiso. So I just broke it up into 3.
You're actually very close, Ben. Very close. Gary, do you have a guess?
I do not know the answer. I'm going to be honest. I should know the answer to that, but I do not know the answer to that.
All right, I've stumped you both. Awesome. Paradiso stands for parallel direct solver.
Parallel
direct solver. So you got the solver, and I think, what did you say? You said pair of something's all right, or partial or something. Anyway, you were pretty close, Ben. So well done. Parallel direct solver. Yeah. All right, Gary. Let's hear yours.
Okay, I got an interesting one for the first one. What is the only feature ever added to HEC-RAS that is site-specific and not generic? Meaning it can only be used in one location on the planet.
Oh. I think I've run into this before, but I'm spacing.
You said which feature?
What is the only feature ever added into HEC-RAS that is site-specific, not generalized, and can only be used at one location in the entire planet?
Is it still in there? Can I ask you that? Is it still in the current version?
It's in the computational engine, but it's no longer accessible from the interface.
No,
but it was in there for a lot of years. So
there are 2 that when you started asking that immediately came to mind, but then I realized they're generalized. But go ahead, Ben.
So I'm going to guess it's something to do with the Eagle Creek area that you grew up in.
You mean Bald Eagle Creek?
Bald Eagle Creek, yeah.
No, it's not Bald Eagle Creek. Good try though. Chris?
All right, so these are going to be wrong, but these were the first ones that came to mind because I know that they're generalized, but I immediately thought of the navigation dams feature that was put in. I think it was originally like for the Mississippi River, but obviously applicable to others. And then I thought, well, maybe that dam breach repair option, because I know that was put in for New Orleans district, right?
Right.
But as far as something specific, I feel like you're going to say, and I'm going to go, oh yeah, I remember that, because I do sort of remember something with a name in it, but let's reveal it. I'm stumped.
Well, you were close because it was for the New Orleans district.
Oh,
And
okay.
it does have something to do with the Mississippi.
Oh, wait, no, I do. I know what it is.
Too late, man. Too late.
It's the Old River diversion.
The Old River control structure. That's right.
Yes.
That is used to split flow between the Mississippi and the Chapalaya to maintain a C30 flow split.
Interesting.
That's right.
Now, Gary, to correct me if I'm wrong, when you download some of the initial RAS files, when you first download RAS from the internet, one of the things you can get is the Eagle Creek terrain data set, correct?
Bald Eagle Creek.
Bald Eagle Creek. Bald Eagle Creek terrain data set.
Yes, you can. Yes.
So would that be considered site specific then?
But that's not a feature in RAS software. That's just a data set.
Okay, I guess that's right.
I meant a computational feature. I should have clarified a little more. Computational feature.
Yeah, that was good. I had no chance. So I'm going to pass on my second one, Chris, because I was busy running the podcast while you were looking this up. So I'll let you go for your second one here.
So, okay, so my next one is I mean, it's sort of RAS related. It's more RAS team related. Okay. And Gary should know this. And Ben, you might have a guess on it. In fact, Gary, this should be in your calendar somewhere. But what was the month and year that I started at HEC?
Oh, come on. Why should I know this? Let's see.
Well, you were just talking about this on the drive over to Eastern Oregon. So
yeah,
my guess is going to be 2002. I don't know the month.
Okay.
I'm going to say 2000. Oh, hang on a second. I have a way of figuring this out. Because you know how I have a way of figuring this out? Because you're the drummer in our band.
Yeah.
And the last
when was our album released?
So it was probably 2001 or 2002. 2001, I think. I'm gonna go with 2001 you started. I don't know.
Have a guess on a month? Take a guess.
I'm gonna say spring, So let's say June 2000.
Oh my gosh, Gary, you're so close. You're right about spring. It's May 2001.
Oh, okay, very cool.
May 2001. Nice job. And Ben, I'm impressed because this was back when you were in maybe kindergarten or something.
I think it was in third grade. Sounds right.
Third grade. Okay. Yeah. Long before you started your HEC-RAS days, but still. Anyway, yeah. What did you have a second one, Gary?
I have a second and I have a third even.
Okay.
Let's see it.
So the second question is, how many official releases of HEC-RAS have there been, not including beta versions?
And okay, define official. What is an official release? Is that
1.0 was an official release?
Well, is like
5.07.
Was 507 an individual official release?
Absolutely.
Okay.
Yeah.
Oh my gosh. Okay. I'm gonna have to just take a guess.
We're not going with beta versions though.
Yeah, I'm gonna have to guess.
I'm gonna say 22.
Let's see. I'm gonna say I like that number, Ben. And I hadn't thought of a number first, so I'll be honest. So I'm gonna use your number. And I'm going to play.
You're going to
Price is Right rules here. And I'm going to say 20. What did you say? 22?
I don't know what I said. I don't remember.
You said 22.
Oh, Gary, come on.
I'm going to say 23.
Guess what? I should really give this to Ben, but it was 23. Price is Right craves you.
That's so funny. Ben, well done, man. I have no idea what I would have picked if you had
you came up with 22 really quickly. I thought you guys were going to start thinking, okay, 1.0, 1. Counting them up, but you didn't even count.
I just thought, I was thinking, we're up to 6.2 now, so 6 main versions, and then maybe about 3 releases per, and then a couple extra. So.
Yeah, that 5 version, 501, 502, all the way up to 507. There was a lot of 5s.
Yeah.
Yeah.
Hey, Ben, have you ever seen a screenshot of the very first release of HEC-RAS, the main window? It's kind of funny.
Sounds terrifying, though. I'd probably be scared.
It's pretty funny, but it's very similar.
It doesn't look that different. I mean, it's funny.
Well, it's like really short. It's really narrow, and then it had to expand out with all the features over the years, right?
Hey, we don't size shame here, Chris. Come on.
Hey, Mark Jensen and I painstakingly drew all those icons and and all that stuff on that first version. So. All right, I got one last question.
Go ahead.
And this is kind of similar to what Chris asked, but when was the exact date, month, day, and year of the very first version of RAS release, not beta version 1.0, and why was it on that date?
Oh, version 1.0. And there's a reason it was on that date.
Yep.
I'm gonna
probably
say
Gary's birthday.
No, it wasn't my birthday.
Let me think.
I'm gonna say June 1st, 1990.
I am going to say, yeah, I can't think of I mean, even if I thought of what the occasion was, I wouldn't know what the date was, but I was thinking maybe it was like on the anniversary of the founding of HEC or something like that. But I don't know what that date is. So I'm going to take a wild guess. I think I'm close on the year. As far as month and day, I have no idea. So I will say January 8th, 1994.
Okay. Well, the first beta version went out in 93. The second beta version went out in 94. The first version went out in 95.
Okay.
And it was July 8th of 1995. And what's significant
I had the right day anyway.
Yeah, you had the right day. What's significant about that was my 10-year anniversary of working at HEC.
Wow.
So I kind of close to that date. So I kind of forced it to be the first version to go out July.
Okay.
So the first version was released on your 10th anniversary, and your last day of work at HEC was released as 6.0. So
yes.
Okay, that's kind of cool. A couple of good bookends right there, huh?
There you go.
They should just rename the software HEC Gary instead of HEC-RAS. Cool. Awesome. Well, that was really fun, guys.
Yeah, that was cool. That's very interesting. I didn't realize it took, you had 2 beta releases before the full release of version 1 came out.
Yeah.
And yeah, that was just steady flow, right?
Yeah. The reason it took so long is that I knew right away that if we weren't able to reproduce pretty much all the features of HEC2, people would not use it.
Yeah.
And because that's just life, right? They'd say, well, that's nice, but it doesn't do this, it doesn't do that. So we really held off until we had not every, but like 98% of the features that HEC2 had before we released it. Plus, obviously, a graphical user interface and graphical output and all kinds of other computational features that were newer. So,
yeah,
sweet.
That's really cool.
All right. Well, without further ado, let's tie into the technical topic for today, which is going to be about utilizing HEC-RAS for tidal modeling. This was actually a question that we've gotten from a few different users. It's also one that when Chris and I first got, we were like, don't know a ton about it. So Chris spent some time kind of diving into the model, experimenting with some things, and he's going to show us some examples of some things to consider when you're building a tidal model. And then Gary's going to look at what Chris did and tell us what we did wrong. So, Chris, I'll turn it over to you.
Yeah. So I've been doing tidal modeling for a long time, and I've had many conversations with you, Gary, about, things, best practices, things to look out for, certain settings that are important, things like that. And so I kind of had this baseline background knowledge, but I never really had an opportunity to explore these different techniques and different ways of setting up your computations so that you get the best out of your tidal modeling. So I thought I'd put together just a real simple flume type of model, and I'll show you what it looks like right here. And zoomed out, it just looks like a straight line, but this is actually my 2D version of it. And if I zoom in, like down here on the downstream end, the tide side, you can see it's actually a 2D model here. I'll get even closer. So it's made up of a lot of cells, but it's a very long and narrow prismatic channel, basically a trapezoid that just goes for, I think, 100 kilometers upstream. So very overkill, but I wanted to make sure I could apply this to a lot of different types of applications. There's also a 1D version of this because I looked at both 2D and 1D modeling. And so the 1D obviously is made up of cross sections instead of the 2D mesh. So I'll show you what that looks like here. Okay, so here's my 1D model. And in fact, when I wanted to build the 2D model, I used the 1D cross sections to generate a terrain, which the terrain you can see behind the cross sections here. So this terrain is actually a surface developed from these cross sections. And then I use that surface to extract terrain onto my 2D mesh for the 2D version of this. So got this very simple thing. All we've got on the downstream end is a simple idealized tide cycle. So if I open up the unsteady flow editor, you can see we've got a stage hydrograph on the downstream side. And I know this because we just asked Gary this a little earlier, but this is the best way to simulate a tide is with a stage hydrograph. So some people try to force a flow hydrograph. It's a little bit tricky. Plus, how do you determine what the flow is? For one, maybe you have a gauge, but it's better to put a tide cycle in with stages. So here's my stage hydrograph. You can see it's, let me make this a little smaller so you can see the whole thing. It's a diurnal tide, meaning you have 2 peaks and 2 troughs in one day. And I know, Gary, I know you're going to say this, but the 2 highs are not the same every day and the 2 lows are not the same every day. It changes, so I understand that. This is a very simplified version of a tide cycle. So I just put that in, and then base flow on the upstream end, just a base level 10 cubic meters per second. Okay. Now, my question, Gary, and this is what I want to get from you in this, is what are some of the important computation settings? What are important equations to use? What are some of the things you want to think about when doing a tide that maybe are not so important in just regular river modeling?
Well, you know, tide modeling is true wave modeling. And
yeah,
when you do kind of this kind of wave modeling and wave propagation, you really got to pay close attention to cross-sectional spacing or cell spacing and time step, first of all. So you need a small enough cross-section spacing or cell size that you're able to pick up the dynamics of the wave rising and falling accurately. And you're not numerically attenuating it because your distances are too far apart, A. Then B, your time step, okay? If you're using too large of a time step, then you're going to attenuate the wave as it moves in just because your time step's too large. So those are first and foremost. Then after that, there's a parameter called theta in RAS that whenever you do tidal modeling, you need to evaluate theta. And in RAS, theta is set to 1 by default because a theta of 1 gives the solution the best chance of solving stably. Right, there's that theta implicit weighting factor. And we set 1 because reality is in real world modeling, you know, away from tidal modeling, most rainfall runoff types of floods, theta of 1 gives you not only the most stable answer, but gives you a very accurate answer. And making it less than 1 really isn't necessary for most situations. Where it does become necessary is when you have highly dynamic situations, whether it's like a dam break flood wave or a tidal boundary condition and or flash flood, or you're opening and closing a gate really fast. So where you have really rapid changes in flow and stage and velocity over short distances and times. And so this theta factor changes how it weights the derivatives, the spatial derivatives, which we could get into. And in theory, the actual theory is that a theta of 0.5 would give you the most accurate answer where you're weighting. Yes, let's talk about this diagram. Let's explain what this diagram is. So this is what's called the space-time diagram. And on the bottom is going horizontal is space. And let's think of J as a location, J as a cross-section, and J plus 1 as another. And then vertically is just time. So let's think of N as the current or the previous time step that's already solved, and N plus 1 is the time step we're solving for. So down at j and j+1 time n, let's say we already know the water surface, the velocity, everything, okay? And now we're moving forward in time to n+1, and we're trying to solve for the water surface velocity, everything at the n+1 timeline at all space. Well, by default, RAS is going to compute derivatives for change in velocity, change in pressure forces spatially, and change in friction forces spatially, based only on the currently solved timeline, n+1. So it has to make a trial, okay, and it gets those velocities, and then it can get the change in velocity and change in pressure forces and change in friction, and put that into the momentum equation and solve it.
Just to clarify, Gary, you said n+1. You meant the current timeline is n, right?
Well, the solved timeline is n. Now we're going to solve for n+1. So yeah, n+1 is the unknown timeline. N is the known. We already have an answer. Okay. Yeah. So the theory about theta, though, this is what's called a box scheme. And the box scheme, if you go and look it up and look at the theoretical analysis, and we're not going to get into all the details, but in the theory of it, if you actually weighted the derivatives at n+1 and n equally, in other words, theta was 0.5, that's the most accurate answer for tracking how something changes with respect to time over the distance. And if you think about it, think about velocity changing with respect to space and time. Knowing the velocity at Jn, and then the velocity, you're trying to get to how that velocity moved through that space over time to n+1, it makes sense that weighting those derivatives equally from the new timeline versus the previous would give you kind of the most accurate representation of what happened over the time step. But unfortunately, numerically, it turns out using theta 0.5, while it's the most accurate, it's also the most unstable. Okay, and unless you use really strict time steps, it has instability problems. Whereas theta of 1, you're using derivatives based on the current timeline only to see what happened over the time step, isn't as accurate, but it's way more stable. And so that's why in RAS, we default to 1, but for certain conditions, we talk about that you should really investigate moving theta down towards 0.5. In RAS, we don't let theta go to 0.5 because we know it creates some instabilities. And we've done lots of theoretical testing on this, and theta of 0.6 basically gives you the same answer as theta of 0.5, but it's just a measure more stable. So in RAS, we only allowed you to go to between 0.6 and 1 for theta.
So you're in this region right here, right, Gary?
Yeah, exactly, for theta.
So
yeah.
theta equal to 1 would be it's using the n+1 timeline to develop the derivatives.
The spatial derivatives. So you just be taking spatial derivatives, right? You'd be taking the velocity at Jn+1 and the velocity at J+1 n+1, and you'd be looking at that change in velocity over that distance. Same thing with the pressure forces at that point in time, and same thing with friction losses at that point in time.
So here's a question for you, Gary. Why or how in the world are you going to use n+1 if that's in a future time where you haven't computed it yet?
Well, it makes a guess at a water surface based on the previous derivatives. Okay, so it's kind of got a slope projection already from the previous timeline, and it uses that as a first estimate of what might change between the previous time step and this new one, and that's the first trial. Sometimes that works out great, and it solves it within the tolerance. Says, oh, good enough. I'm moving on to the next time step. A lot of times it's maybe not good enough, and it says no, that slope projection wasn't accurate enough. So things are changing. Maybe the flow rate has a significant change, or something like that over the time, and so it has to update those guesses and try again. Okay. And
this is all thrown into the matrix solution, right?
Yeah, because it's solving all of space at each time step. So the questions are written for every location, and there's dependencies upon, cross section next to the other cross section for calculating these derivatives. And then it's thrown into a matrix, and then upstream you obviously have a known flow coming in at the new time step, and then downstream we generally have a boundary condition. And in the case of tidal, that would be a stage, right? You already know the stage at the new time step because it's your boundary condition.
Yeah. So there's iterations upon iterations, and there's matrices being developed and inverted all throughout. So all of you RAS users out there, next time you complain about how slow your models take, keep in mind what's going on in the background here.
Yeah, there's a whole lot of numerics going on just to do this even in 1D, then let alone 2D.
Yeah, that's great, Gary. I appreciate the explanation of that box scheme, because and it can be applied to 2D modeling as well, right?
Yeah, same concept.
You just have two spatial directions instead of one, right?
Yep.
So it's a cube instead of a box, I suppose.
Yeah.
Yeah. Oh, very cool. Okay, well, why don't we get into the model that I built here, and you can tell me what I did wrong or what could be done better. But basically what I did is I set up several different plans, and I wanted to compare different thetas, because theta is important in tidal modeling, as Gary just mentioned. I also wanted to look at things like, well, what about 1D versus 2D? How's that going to change the results, and why would they be different? And then diffusion wave versus ELM, which is the more commonly used full momentum version of the same canonic equations that are built in. And so wanted to take a look. So let's, Gary, why don't we look at, how about a 1D model first? And I'm going to just compare theta equals to 1 versus theta equal to 0.6, just to see what the differences are. And what I've done here is in this model, I've drawn some profile lines so we can extract some data off of it. And I'm going to take a look at a transect that's halfway up the length of this model. That's why it's called transect 50. It's halfway up, and just look at the flow hydrograph differences between those two. So we'll pull that up here, and you can see right away there's some differences between theta equals 1. Oh, actually, I've got some other plans on here. Hang on, let me uncheck those first. Some of those 2D plans. Okay, let's go back to that. Okay, so with theta equals 1 in 1D, zoomed out, not a whole lot of difference, but if I were to zoom in, you can tell me what you think about this, Gary. I'll zoom in pretty close here. There we go. Now we can see the differences, and it looks like way out on the fourth, I think the fourth cycle, tide cycle, it's about maybe 1/10 of a foot different, or a meter, sorry, 1/10 of a meter difference. So 10 centimeters, maybe not a huge deal, but significant enough.
Yeah, the other thing about this is I'm betting that you picked a really good cross-section spacing already and have a really small time step.
Yep.
So you've already taken out of the equation diffusion due to, excuse me, is that a word, due to?
Let's not get too technical, Gary.
Yeah.
Just in case some people aren't following.
Yeah. So you've kind of taken out of the equation already any kind of attenuation or numerical diffusion due to the space distance being too long for the wave being modeled and the time step. And when you do that, differences because of theta become smaller too. So in other words, if we had used a larger cross-section spacing and a larger time step, we might have had some numerical fusion we didn't even know about because we had too large of a cross-section spacing and time step, right?
Yeah.
But then if we just did the theta test only, we would probably see even bigger differences because of theta also at this point.
So shorter or closer spaced cross sections and closer spaced cell centers is a good deal, or good thing to work towards here. But along with that, you've got to have a correct time step too, meet the Courant number condition, right? Right. Yeah. So I know everyone's thinking, well, how close do I need to make my cross sections or my cell centers? And I'll answer that and let you, Gary, after that. But I mean, you really don't know for sure until you test out some different spacings and see how the results start to converge. Is that about right, Gary? Yeah, that's really the only way to do it. And what's funny is back when computers were really slow, engineers used to do that on a regular basis. They used to test cross-section spacing and time step, and it was always part of their study to do that, to make sure that they weren't getting numerical diffusion, okay? It seems now that computers are so much faster, kind of people are kind of forgetting that part of the fact, do I have enough cross-sections? Are they spaced close enough together? Is my time step small enough? And you're exactly right. The only way to check that is to do a couple of trials. So let's say you have 500-foot cross-section spacing. Well, you sure as heck should run a run with 250-foot spacing and an appropriate time step to go along with it for a Courant number
based on that smaller spacing, and then compare that to your 500-foot larger time step run. And if there's a significant difference, that tells you, okay, your 500-foot wasn't good enough. And then you don't know if your 250 foot's good enough unless you cut that in half, maybe again, okay, and go down to 125 foot. But it should converge as you get to shorter spacing and smaller time steps. The numerical diffusion to the spacing, cross-section spacing, or cell size, and the time step should be diminished towards 0. And that's called space and time convergence, okay? And that's when you really know, okay, I've got a reasonable spacing and a reasonable time step. I can move forward from here.
And in theory, you should see your theta differences decrease along with that decrease in computational node spacing, right?
Yeah, because as you're reducing the time step, the change in the derivatives is less over and reducing the space, the change in derivatives is getting smaller, right?
Yeah.
And weighting them between timelines, the timelines are closer together, that's smaller. So theta should become less of a dependency. It might still be a dependency depending upon the problem, okay, and how dynamic the wave is. Like if you have a dam break that goes from nothing to 1 million CFS in 5 minutes, well, theta is probably still going to be a factor, okay, and you might want to mess with that and check it.
All right, very cool, very cool. Well, let me move on to another example. Let's compare 1D to 2D, and I'm just going to go with the theta equal 0.6 because it's kind of where you want to be for a tidal model. And I'm going to go to a 2D, but I'm going to use diffusion wave first. Now I've got this set to 10 seconds for my diffusion wave model, and it's all based on trying to get a Courant number down to 1. And I know that's tighter than you need for diffusion wave, but I wanted to just kind of take that out of the equation altogether. So we've got 1D theta equals 0.6 compared to 2D diffusion wave theta equals 0.6. And let's see what the difference is here. Now we got a big difference. So this is telling me that there's something different, obviously, between the 1D and 2D equations, besides just the additional dimension, because this is a very one-dimensional model, right? It's just a trapezoidal flume. So why would there be such a difference between these two, Gary?
Well, in the diffusion wave equations, we don't include the time derivatives. The change in velocity with respect to time. Okay, right. We're only including or change in velocity with respect to distance. We're only including the pressure differential and gravity force and friction forces in diffusion wave. Those are the forces. So you don't have those velocity terms in there; they're dropped out. Okay, so it's quite a bit simplified. And if you're working in a river system where the slope is fairly steep, well, then gravity and friction are really controlling almost everything. And that's where a diffusion wave method will shine, is in steeper slopes, okay, or at least medium slopes. But once you get into flatter slopes and you have more kind of like wave propagation, and what has happening downstream affects upstream, and especially if you get into tidal, tidal coming in is all about velocity, right? As far as how much it's going to propagate up and propagate back. Okay, so if you don't have those velocity terms and derivatives, then that alone is why you're seeing this difference in really more so than anything related to time step or theta. It's the fact that you don't have those velocity terms.
Yeah, I've always heard that, when you get into the really flat systems and, with backwater being a dominant part of it, and what's more backwatery than a tidal type model, right, is those inertial terms on the left hand side of the momentum equation are extremely important, and diffusion wave gets rid of those. So that's why the diffusion wave is not a good option here.
Yeah, so, and this also is for just a simple trapezoidal channel. Okay. I think in natural channels, you should probably even show more difference.
Yeah. So let's then look at a full momentum solution. So I'm going to just switch off the diffusion wave, and I'm going to turn on the ELM, theta equal 0.6 still, and let's see what we get here. Okay, it's better, right? There's still some difference, but it is better.
Yeah, I mean the timing and the shape is closer. There is a little bit differences in the peaks and the troughs. Okay, and the ELM is the Eulerian-Lagrangian method, and that was our first 2D method we came out with. And it uses what's called tracking to track upstream to find the change in velocity. So you have a face at a cell, and it tracks upstream to find where and spatially did this velocity start, and how far did it travel over the time step, and what was the velocity at the beginning. Okay, and that tracking, unfortunately, it has to do things like track back faces, but it also has to do like estimate velocities in the middle of cells. And so there's some numerical averaging happening. And because of that kind of stuff, you can get some numerical diffusion of that velocity term, that inertia term. Okay. In most real world models, rainfall runoff and so forth, you're not going to see much, especially as you make the cell size smaller and the time step smaller. But where it does start to show up is kind of these difficult problems that are highly velocity driven. Okay. And you'd see it also at, like, for dam break floodways, you might see it a little, but real tight contractions and expansions where you have rapid changes in velocity versus distance. Then the EM method is just the Eulerian method. That method we added in 6.0 because we realized that this current method that was in the original RAS 5.0 had some locations that, it had some numerical diffusion. And that method was really developed to be A, fast, and B, stable. Those were kind of like two of the driving forces. It's not that it actually was important. Of course it is, but we really wanted fast and stable, especially for wetting and drying, which RAS does really well, okay, for 2D, et cetera. But then we decided to add a third equation set, which is the EM method. And there the whole goal is, we want momentum conservation, period. And it's an explicit method, and you have to use smaller time steps in general than the ELM. And it evaluates the velocities only locally around the face, halfway upstream and halfway downstream. And you can read about that in the hydraulic reference manual. So it doesn't have to track back in space and interpolate and estimate velocities, not estimate, but interpolate velocities. So it does a much better job at conserving momentum. So I bet if you go to turn on the EM answer, it should be better than the ELM for this problem.
Yeah, let's do that. And before I do, the L in ELM is for Lagrangian, and that's the tracking part of it, right?
Right, the Lagrangian method.
Yeah, the Lagrangian part of the ELM, and then taking that out, it gives you the EM. And let's see what we get there. So I've done the same thing using the EM. We'll go to theta equal to 6.6. By the way, I had to reduce the time step to make it work because, Gary, you mentioned it's a lot more strict with Courant numbers and not as stable as ELM. So I had to get the time step down a little bit to make this work. But let's see what we get here. Okay. Well, so it's still a little bit of difference between 1D and 2D.
Well, the 2D is higher in this case.
Oh, did it actually dip below? Oh, yeah, I didn't even catch that. Okay. So let's turn on. Let me turn
higher in the other case too. Turn the other one on. Turn all three of them on.
Yeah. Okay.
I may have flipped that in my brain.
Well, let's make sure we got that right. Okay, so 2D EM is the dark blue line. Well, this is not helping. I can't see where the green line is.
You gotta zoom in.
So let me zoom in really close here and see if we can pick that up.
Is it not showing it for some reason?
It might be on. Could it be on?
I think it's under here.
I think the ELM and the EM are the same. Looks like it's the same.
No. Okay, there we go.
Virtually the same.
So this is showing the difference between EM and ELM. The EM is higher a little bit, and then the 1D is, down here, a few meters below that.
So in this case, yeah, do the full plot. Okay, so this is upstream. So in actuality, the 1D is showing more attenuation than the 2D solutions.
Yes, it is. Yeah.
Yeah. But it might also get into, is your cell size the same as the 1D cross-section spacing?
No.
That's
Cell
right.
size
Your
is
cell size is a
small.
lot smaller, right?
Yeah. Yes.
So exactly. And then you had to use smaller time steps also. So here
Yes.
it's kind of a case of really it's because the 1D cross sections are much farther apart and using a larger time step. You could probably get a closer 1D answer if you went down to a much smaller cross section spacing and used, a 10-second time step. You'd get closer to the 2D answer then.
Yeah, that is really interesting. And I think it just really solidifies the point here, Gary, that especially in a tidal zone, of course, I'm doing a very idealistic flume model, which you would never see in real life out here, which probably adds some additional problems, as far as the answers being different. But you got to look at these things, right? You got to test things out. You can't just build your model and take the results for granted that they're correct. And then what would you say, Gary, would be the most important things when you're thinking about doing a tidally based model in an estuary, something to think about?
Well, first of all, is you got to have your boundary condition. If it's ocean driven, I like to put my boundary condition out in the ocean.
Yeah.
Okay, and the reason is, and I like to have my terrain like ocean level and then coming up, because then what you're going to get is you got that wave propagating up and down, but you're also going to get a convergence of the terrain vertically, and and then that'll help capture the velocity acceleration that occurs when that wave comes in, right?
Yeah.
And so that'll give you more accurate velocities coming in. If you just put the tidal boundary condition in the middle of the bay or estuary, yeah, it's still going to have velocity go in and out, but it might not be quite as accurate. Okay, so but the important thing is where was the data measured? Was it measured in the middle of the bay? Then of course you use it there. But if it's an ocean gauge, then that's out away from the boundary, okay, of the coast. And so I like to add some terrain out in the ocean and then put that boundary condition out in the ocean if it's an ocean tide gauge. Okay, so that's important. And then as we talked about earlier, cross-section spacing or cell size and time step is then the next most significant thing. And then checking theta after that. But generally, I found that if you do any kind of tidal modeling, you should use theta less than 1. By default, I usually set theta to 0.8 if I'm doing any tidal modeling, just even to start. And then I'll check moving it down to 0.7 and 0.6 to see if it makes any difference. A lot of times it doesn't. 0.8's sometimes good enough. Sometimes it does make a difference. But definitely every tidal kind of modeling ever done, theta of 1 doesn't work good. Because what happens is as that wave comes in and moves upstream, it diffuses it, and it doesn't show the influence of the tide going as far upstream as it should. Okay, because it's going to, you're just showing kind of one location here, but somewhere way upstream, the worse theta is, or if your cross-section spacing is too large, your time step's too large, the influence of the tide is going to diffuse out quicker, and it's not going to show up farther upstream. And a lot of these systems around the country, like, the Columbia River, I mean, at low flow, you see a dominant tidal signal right up there at Portland. That's a long ways from the ocean. Okay, same thing down here in Sacramento, we're a good, I don't know what it is, I'm going to say it probably wrong, but 50, 60 miles from the San Francisco Bay by the ocean, by the river, and there's a strong tidal signal at Sacramento during low flow.
Oh, wow.
Now, for really high events, that gets washed out, right? Because the flow is so high in the river and dominating the water surface and velocity downstream that the tide may not be that important. And especially maybe for like a dam break. If you're doing a dam break model on a coastal area, the dam break flood wave is going to dominate the water surface all the way out to the ocean. And the tide might not even affect it. So it depends on the problem you're modeling also.
Yeah. So I kind of see this as, setting up a model like I did here as a flume. It's got very little base flow coming from the upstream end that I'm really magnifying these differences. I think, correct me if I'm wrong, Gary, but having more base flow coming in, that's going to mute the differences, as well as having a lot of difference in terrain and variation in terrain and shape of the channel as you go down is going to also have a muting effect on the differences.
Yeah, one thing about base flow though, it can work kind of both ways. Is deeper water allows waves to travel faster, right?
Yeah.
Yeah,
That's
so
true.
if you had really deep water, you might get higher velocities.
Interesting.
Yeah.
Wow.
So then shallower water, less effect,
Yeah.
more frictional based.
Right.
So
Well, now we saw very little difference between ELM and EM in this particular case. Would you recommend EM for a model, a typical estuary type model, or are we still doing ELM for that, in your opinion?
I think you have to try. I don't want to say A or B because I'll be wrong in some instance, right?
Yeah.
I would say in general that either one will work fine in most tidal situations, but there's going to be some where the EM might work better. And the only way you're going to know that is to try them both. But the great thing is it's so easy to do in RAS. Create a second plan, switch to the other solver, maybe adjust the time step a little bit, run it, compare the answers, and then you have the answer for your specific problem. But I think most cases ELM, the original one, does quite well. And as you can see here, the differences were small, okay, for the 2D one.
Right. Right.
Yeah.
Well,
but it could be site specific though. So I think the new solver is really important where you have sharp contractions and expansions in your river system, because the spatial variability of the velocity is dramatic, and that's the tracking method. It's hard to track where the velocities are coming from in sharp contractions and expansions, okay, and where they're going. And that's where the original method, the tracking, you start to get a little bit of a numerical attenuation of the inertial terms because of that.
Interesting. Yeah, I wasn't aware of that. So if what you're saying is if the advective acceleration, contraction, expansion is dominant, that EM may do a better job than ELM in a river.
And again, you gotta test this and know how significant it is. In some cases, it might not be significant.
Right. Interesting.
Yeah.
No, that's great to know. So Gary, before we wrap this up, I just want to throw one thing out. And as you know, I was also doing some tsunami modeling along with this. I didn't really want to share any of that today because it's not ready. But the tsunami is basically the same thing we're looking at here, only just a very extremely dynamic version of it. So, you have going from, say, a stage of 0 to maybe 10 meters, 15 meters, or even more in the span of about a minute or so, and watching that progress upstream. Do you have any thoughts on what pitfalls you may run into trying to do tsunami modeling and how some of that may affect some of the decisions and how you set up the model?
I have to say I've never used RAS for tsunami modeling, so I don't consider myself an expert on it at all. But I don't think I have any tremendous insight into tsunami modeling. I'm sure there's lots of people out there that have much more insight than I do. But I would imagine that's definitely an area where you want the terrain out in the ocean, okay, and setting your boundary condition farther out. Because when that tsunami comes in, you want that convergence and that acceleration of velocity coming in. And again, some of the same things we talked about here: smaller cell sizes, smaller time steps, et cetera, and then test the sensitivity of it.
Yeah,
that's the key. The key really is testing the sensitivity of the spacing, whether it's 1D cross sections or cell size, the time step, and then in this case, theta. Okay.
Yeah, some of the stuff that I did notice in my preliminary modeling of the tsunamis is even in a profile view. So in a profile view for what we're doing here, just a regular tide, it's pretty boring. There's not much to see. I mean, we could turn it on here. I could just plot let's just plot a water surface profile like this. And, I can animate it and it's pretty boring. It's just the lines going up and down, pretty flat. But with the tsunami, you see a very clear and distinct wave and you can watch it propagate up this slope. And there's some very clear differences between diffusion wave and ELM and EM, as you might imagine, but also in the different thetas. And you even get some pretty interesting artifacts on the front end of that wave. You'll get some instabilities, kind of a up and down jagged pattern in the wave front, whereas the rest of it may be stable, but just the front of it has got a lot of bouncing around. And so anyway, I hope to present that a little bit later. Maybe we'll get you on to talk about that too, Gary.
Well, tsunami modeling, the key right there is the wave is much more dynamic than a tidal, because you're going from a lower stage to a much higher stage over a very short amount of time.
Mm-hmm.
Chris, did you include Coriolis in any of these simulations?
I did not.
But in theory, if you were modeling a larger bay or river confluence with the ocean, that might be actually one of the few situations where it's worth turning that on, right?
I'd love to hear what Gary has to say about that.
The answer is yes, but I would also qualify that it's more so true if you're farther away from the equator, right? So if you're up in Alaska, Coriolis might be an important parameter to turn on.
Understood.
Yeah.
I've always been of the opinion, Gary, on the Coriolis, and you can correct me if I'm wrong here, is that in a typical river, you're probably not going to see much of an effect. And obviously the effect will be more pronounced further away from the equator, but it's more large bodies of water where you really see Coriolis. Is that correct?
Yeah, absolutely.
Okay, good. Because that's what I've been telling people.
Yeah. And obviously tidal modeling of certain segments of the ocean would be included in that. So
right. Absolutely.
Yeah. Very cool. Well, Gary, man, that has been fantastic. I've learned a lot already, and just our little discussion here. And so I'm hoping everybody out there has picked up on some best practices, some little theory knowledge as well, which is always good to have. Helps you make better decisions in how you set up your model and how you troubleshoot it. So thanks, Gary. Appreciate that.
Thank you for having me on. It was fun. It's always fun hanging out with you guys. So
absolutely, we'll try to do it again. It's fun to mix up the voices that folks hear on this, especially if it's a voice as informed as yourself, Gary. So we appreciate you taking the time to share your thoughts with us and the audience. Anything else, Chris, before we wrap up?
No, I just appreciate Gary coming on. Gary, hope to see you in person here sometime again soon. And I've been trying to twist Gary's arm into teaching me how to fly fish, so I can be ready to retire here soon. But
hey, I am ready.
One of these days.
I am ready. We just got to plan on a weekend to meet somewhere and just do it.
Yeah, I'm just gonna have to come down to Davis. We'll go do the American River, or what's your other one that you like to go up to Shasta, right?
Well, the Sacramento River, upper Sacramento River above Shasta is a river I fish a lot for trout. Okay. But then I fish a lot up in the mountains. And when you said American River, I fish the small streams way up in the mountains a lot for trout.
Oh, the East Fork or the South Fork or the Middle Fork kind of stuff. Yeah.
Good.
Yeah.
All right. Well, awesome. Cool. Thanks again, Gary. Appreciate your time. And I will give one last shout out here. My Gonzaga Bulldogs have a big game tomorrow. So go Zags.
Let's get it. Let's get that title this year. All right, Ben? Come on, man. It's about time.
All right. Awesome. Well, this has been Full Momentum in HEC-RAS podcast. Thanks again, everybody.